At this point, you should have printed out this this handout. As of right now, the atomic model, we have gotten to the point of Bohr, who says that the electrons are not anywhere outside the nucleus, but in discrete locations called energy levels. And specifically, uh, atoms only absorb a specific amount of energy, and that amount of energy is exactly equal to the energy that the electron needs to obtain so it can jump up to a higher energy level, making the atom in the excited state, and instantly jumping back down, releasing all that energy to get it back into the ground state. But it's a specific amount of energy. Well, there's an issue here is now I need to explain to you a little bit about energy, because energy is not always what people think they are or think it is. In this discussion, including the discussion with the atom, we're using light as a form of energy, and specifically, we're basically saying light and electrons are very similar to each other, going at the speed of light, and both electrons and light, and that light has no energy, and electrons have very, very small amounts of energy. So therefore, this explanation is using light, but we're going to also apply it as an electron when we talk about the atom. Around 1900, there was a big issue in physics. What is this thing called light? And there were two camps. Light is a wave, and light is a particle. And light is a particle, a guy named Max Planck was kind of the lead person on it. Not that there wasn't a bunch of other people. but light as a wave and light as a particle are two totally distinct things. So this table provides a little explanation of what they are. Light is a wave, as you know, like a water wave, is continuous and cannot be broken up into a smaller part. The analogy I use is water. Somebody's going to squirt you with water. The water is the energy that's coming at you. And light as a wave would be a garden hose. The water is coming at you through a garden hose. It's a continuous thing. You can't get half of a stream of water from a garden hose. And when you have light as a wave, there is actually an equation. It's called the light equation, which is the speed of light is equal to F times lambda. Lambda is a backwards H. So you've taken H and kind of put it backwards. That's what lambda looks like. It's a Greek letter. C is the speed of light, which we're going to use as 3.00 e to the 8th meters per second, or another set of units, meters times hertz, and you'll see why I use that in calculations. Frequency basically is if you're standing at a point and a wave is going by you, counting the number of waves going by you in a second is the frequency. And it's usually measured in hertz, where hertz is 1 over second. And 1 over second is the unit for frequency, where 1, instead of saying waves, they use 1. I don't know why. You will actually have a more in-depth explanation and calculations on light as a wave once you click on that link, light as a wave link, and I'll explain to you various things about light as a wave, electromagnetic spectrum, how to do the calculations, etc., etc. The other camp was, as I said, kind of run by Max Planck, and what they felt light was it wasn't coming at you like a garden hose. The water is being light. It actually came in discrete packets, which he called quantas. For all you Star Trek fans out there, the photon. This is where the photon torpedo came from. It's the photon is actually the basic unit in quant is called quantum mechanics. Um, the basic quanta unit is called photon. Again, so what the when you are going to get squirted with water, you wouldn't be using a garden hose in this analogy, using light as a particle, but actually using a water balloon. So water balloons would be coming at you, and the size of the water balloon, as in how much energy is coming at you, i.e., how much water is in the balloon, is determined by the volume of the balloon. That's why you would duck if there's a big water balloon volume versus a small water balloon volume. With his equation, what he said was that the energy of the light, or in this case, the energy of electron, is equal to a constant times its frequency. So instead of me looking at the volume of the balloon, you would look at the frequency of light. The energy unit is joules. Planck, there's actually H is called Planck's constant. It's 6.60 times 10 to the minus 34th joules per hertz. And the frequency, as we said before, is in hertz or 1 over S's. Now, again, you're going to have more explanation when you click on the link below. Light as a particle. So they had two camps, and the story goes that there was a conference in Europe, and you have two different sides, and there was this guy, not as big as Einstein and Bohr and all these other guys, but he said, "Well, you're both right and wrong," and it actually was proved correct. And the guy's name de Broglie, and it's called the duality of light. Light is both a particle, a discrete packet, and a wave, a continuous thing, at the same time. Yes, I understand it doesn't make physical sense, and the way they would explain it is it doesn't make physical sense because we live in what they call a classical mechanical world, Newton world, and these particles don't live in that world. They live in a different world called a quantum mechanical world, which we'll talk about later. So even though it doesn't make physical sense to us, it actually has, it is physically correct. So with that, what you can do is the equations from above, you can relate them to each other, and you can see that they're linked by the frequency. So therefore, you now, what you can do is, if you know the energy of the light, therefore you know its frequency and you know its wavelength. And this will be an important thing when we talk about how atoms and energy interact with each other. So again, you're going to be seeing that in the video. In this case, you're going to click on light as both a particle and wave and how it relates to the atom. So again, what I just explained, kind of as wrapping it up, is that light is actually a little bit more complicated than you may have thought before. It actually has characteristics of both a discrete thing and a continuous thing, and that we're going to use those characteristics to explain how our electron moves outside the nucleus and how the atom absorbs energy and when energy comes to atoms. Okay? Thank you.